The first several examples we'll do in this video, we're giving an equation and we are to compare it to its parent. And the directions tell you what the parent is, but the reality is that your goal is to get to the point where you don't need anybody to tell you what the parent is. You know just by looking at it. And the way you know is that when you look at this equation, it's quadratic. So we're going to compare this graph, or this equation, to its parent graph or parent equation to think about what it would do to the graph. And this one's really simple, but we're going to start on this one with having a question, this sort of a two-part question in our minds, and that is, what's the difference between the equation I'm looking at and its parent? And obviously here that's plus 5.2. And then the second part of that question is, and where does it happen? And this plus 5.2 is outside the square, so that means that it's going to be a direct vertical change on the graph itself. So remember, anytime a number is added outside the function, it moves the graph both in the direction and the distance that the number represents. So this equation moves y equals x squared up 5.2. And you could also call that a vertical translation. That's the more, technically correct terminology. Remember, a translation is just a slide. Now let's take a look at number 4. Again, we see a square, so we know this is a quadratic, so we write y equals x squared. And think about it. I could also write y equals x squared as y equals x inside parentheses squared. So when I say inside, outside, I'm talking about whatever the function does, and this function squares, then the inside of its function would be x. And the one we're given, what's inside is x minus 3. Because that question I should ask myself is, what's different between whichever version of these makes the most sense to you and the one we're given? And there is a minus 3 in the one we're given that's not in the parent, and it is inside. So because we have an inside change, that's horizontal and backwards from what we would normally say. So since I have a minus 3 inside, this moves x squared, or y equals x squared, to the right 3. And then that would also have a more sophisticated name of a horizontal translation. So if you want to be really impressive, you would say we have a horizontal translation of 3 steps to the right. On to the next one, number 8. Again, we're still working with a parabola here because we see the square. And now we ask ourselves, what's different between this equation and y equals x squared? Well, clearly I have a plus 50, which is inside the square, and I have a minus 279, which is outside the square. So the plus 50 moves, just trying to decide whether to say it technically correct or the way it would make the most sense to you. The plus 50 moves x squared, and that's supposed to be a 2, left 50, because it's inside. And then the minus 279, because it's outside, moves x squared down 279, because it's outside. So inside backwards, outside direct. And you could list both of those changes in one statement. Obviously, when we get to number 10, we are no longer comparing this equation to y equals x squared, because we don't see a y equals x squared, we see a square root. So we're going to compare this one to the parent graph of all square roots. So y equals the square root of x. Well, again, what's different? I see a minus 5, and it's inside. So the graph we have moves the square root of x. Remember, inside is backwards. Right 5. On to the next one. Number 12. Again, we see a square root. We know that's what we're going to compare to. Now, this one has a little bit of a little wrinkle to it that I want to make sure you're clear on. So put a little star on your packet beside number 12 because this one really becomes really important. On everything we've done so far, the x has been positive. And as long as the x is positive, you can do exactly what we just did. But anytime the x has a coefficient on any function and you're trying to use this line of thinking, you need to factor that coefficient out of both terms that are there. So we're going to pull out a negative from both the 3 and the x. So that would give us x minus 3 on the inside. And you can prove that's right because if I distribute the negative back, the x would be negative, which it's supposed to be, and the 3 would be positive. So this helps me see the translation. So there's actually two translations that in this version you see, but in the original version you might not see. So these are the ones we have to focus on. So when we ask ourselves what's different, we have to account for the negative in front of x and the minus 3 behind the x. And you talk about it in terms of the negative being factored out of both of them. So our graph, remember a negative coefficient on the inside is a horizontal reflection. We'll start with the proper terminology this time. So we have a horizontal reflection, if I can write, across. And remember, we know that it's going to go across the y-axis because if it's inside, it's a horizontal and backwards change from what we would expect. But we're going to have a horizontal reflection across the y-axis and a horizontal translation three right. And that's the more technically correct way to state that. And I'm less worried about your technical jargon than that you understand these effects. Then we go to number 14. And again, even if the directions didn't tell us, because we see a cube, we want to think about the most basic or parent cubic function, which is just y equals x cubed. And the difference we see between these two equations is that 2 on the inside. So again, inside backwards and horizontal effect. So the difference between these two graphs is that this graph shrinks, and it's backwards because it's inside, shrinks by 1/2 horizontally x cubed. And another way you could say that is back towards the y-axis. Then on number 18, we have a little more complex set of questions in this part of the assignment. We are told to describe how to transform the graph of f into the graph of g. And this is the graph of f, and this is the graph of g. Now, your book didn't graph these for you, so when you get to this set, you need to be prepared to graph these by hand, but I wanted you to have that part out of the way for our video and our example purposes. Okay, so we're not transforming from the parent, we're transforming from f to g. Well, obviously, one obvious translation, or not translation, but transformation, is that g is turned upside down. So remember, to make that happen, or what made that happen was that negative. So you can do this like as a bulleted set of explanations here. We reflect across the x-axis. All right, well, if I took f and reflected it across the x-axis, what I would end up with would be right here. So far we've taken care of the fact that it's upside down. But I need to move it from positive 1 over to negative 3, where it sits for g. So then I would say a horizontal translation. And again, you're thinking not from the parent, but from f to g. We would go back to the left 4 steps, and so we'll say a horizontal translation of left 4. And that's all you have to do for that one. And then on number 20, which will be our last example for this video, same idea, but got a little bit different. I guess you could argue that this would be maybe harder to explain. But the difference between these two graphs is that this graph, remember, because it's backwards, is half the size of the parent, and this graph has an external multiplier, which means it gets stretched vertically. So if I wanted to get this one back to the parent graph, to me on the multipliers it's easier to think of it this way, I would need to, because this is shrunk back towards the x-axis, because notice the parent graph would be at 1, 1, which is right outside, right there on both sides. So that's how much it's pulled back in. It's halfway back to the x-axis. So I would need to get rid of that, and it might be easier to do this, and then we'll try combining them into one statement. But to get it back to that, I would need to stretch. Let's try that again. In fact, let's start out by saying we need a horizontal stretch, and let's abbreviate that, by 2. So I would stretch by 2 to get rid of the fact that it's been shrunk by a half. And then I need to go a step further, because now I need to get that stretch of 4 on the outside, and then do a vertical stretch of 4. Now, to think about this, and I debate about showing this to you, but I'm going to go ahead and show you. There's a property with absolute values that if I have the absolute value of 2x, I can rewrite that as the absolute value of 2 times the absolute value of x. So this is the equivalent to saying 2 times the absolute value of x. And to me, this is the easiest way to see what I was about to say, because remember a minute ago I said we're going to go back and write our 2 transformations into 1. So because of these two, I can do this as a combination, and then thinking of it analytically this way, I could say this is my actual answer, and that is to do a vertical stretch by 2. Because when I write the equation this way and compare it to the equation for g of x, I can see that the only difference is that g of x is double in terms of the vertical stretch. And if that's confusing to you, just pause the video and ask some questions. That's the end of this video.